In chapter 10 of our lecture on linear system theory, we look at a special class of matrices called Hermitian matrices and an important property called positive definiteness. We begin with definition 10.1, where a square matrix U is called unitary if U times U star is equal to U star U is equal to the identity matrix. This definition looks very similar to the definition of an inverse matrix, only that for a unitary matrix, U star, so the adjoint of U, acts also as the inverse matrix of U. For example, the 2x2 rotation matrix that was already defined in chapter 2 is a unitary matrix for any rotation angle theta in R. This fact is easily verified by a matrix multiplication where we multiply the matrix U from the left with U star and we obtain the 2x2 identity matrix because for the diagonal elements we obtain sine squared of theta plus cosine squared of theta, which is equal to 1. And for the non-diagonal elements, all terms cancel to 0. In the same way, we can show that also U star is equal to identity as required by definition 10.1. However, similar to the identity matrix, it's sufficient that one of them, so either U star U or U star, is equal to the identity matrix. For any unitary matrix U, we have the following basic properties stated in lemma 10.2. A, the 2 norm of U times a vector x is equal to the 2 norm of x, or one could say the 2 norm of an arbitrary vector x is invariant with respect to multiplication with a unitary matrix. B, the inner product of U times x with U times y is equal to the inner product of x with y. And finally C, as we've already seen, the inverse of a unitary matrix is equal to its adjoint. The proof of lemma 10.2 is fairly straightforward. For part A, note that the 2 norm of U times x squared is by definition equal to the inner product of ux with ux. By the definition of an adjoint operator, we can pull this u into the first argument as a U star, and we obtain the inner product of U star ux with x, whereby the definition of a unitary matrix, U star U, is equal to the identity matrix. So therefore this is equal to the inner product of the vector x with the vector x, or the 2 norm of x squared. The proof of part B works exactly in the same way. So the inner product of ux with uy is equal to the inner product of U star ux with y. And since U star U is equal to identity, this is equal to the inner product of x with y. And finally, part C follows directly by comparing definition 10.1 of a unitary matrix with definition 2.7 of an inverse matrix. Lemma 10.3 provides an important characterization of unitary matrices, namely its column vectors u1 through un form an orthonormal basis for Cn, and equivalently its row vectors u1 tilde through un tilde form an orthonormal basis for Cn as well. The proof of lemma 10.3 is actually fairly obvious, so let Sik denote the ikth element of the matrix S, which is defined as U star U, and tik be the ikth element of the matrix T, which is defined as UU star. By the definition of matrix-matrix multiplication and the fact that the matrix S is equal to the identity matrix, we have that SIK is equal to UI star UK, which is equal to 1 if I equals to k, and 0 if I is not equal to k. Hence, we conclude that the column vectors of the matrix U are orthonormal, and we have n column vectors, so it follows that the column vectors form a basis for Cn. Exactly the same argument can be made for two row vectors, ui tilde and uk tilde of the matrix U, whose inner product must be equal to 1 if I is equal to k and equal to 0 if I is not equal to k. Hence, the row vectors also form an orthonormal basis for Cn, and we have concluded our proof. Note that due to the characterization of unitary matrices in lemma 10.3, unitary matrices are sometimes also called orthogonal or orthonormal matrices. Next, we leave unitary matrices aside for just a little moment and turn our attention to so-called Hermitian matrices in definition 10.4. Namely, a square matrix H is called Hermitian if it is equal to its adjoint. If instead of working with complex matrices, we are working with real matrices, then a real Hermitian matrix S is also called symmetric, which means that S is equal to S transpose. To illustrate this definition, let's look at a little example of this 2x2 matrix A, and we ask whether this matrix is Hermitian or symmetric respectively. First, note that A is not Hermitian because A star is equal to the complex conjugate transpose, which is equal to this matrix, and this matrix is obviously not equal to A. Second, note that A is also not symmetric in the sense of definition 10.4 because it is not a real matrix. Hermitian matrices satisfy some basic properties stated in proposition 10.5. Here we let H and G be two Hermitian matrices, then A, the sum of H and G, is also Hermitian, B, the product of two Hermitian matrices, so H times G and G times H are Hermitian, and C, if H is invertible, then also H inverse is Hermitian. The proof of this proposition is fairly straightforward and therefore omitted. Hermitian matrices have an important property with respect to their eigenvalues and eigenvectors. First, as stated in Theorem 10.6, a Hermitian matrix H always has n, not necessarily distinct, real eigenvalues. Or in short notation, every eigenvalue lambda I of H is an element of the reals. For the proof of Theorem 10.6, we pick any eigenvalue lambda in the spectrum of H, which means that there must exist a non-zero eigenvector x such that H times x is equal to lambda times x. Now we modify this equation in two different ways. In the first case, we leave the equation as it is, and in the second case, we take the adjoint on both sides of the equation, which yields that x star h star is equal to the complex conjugate of lambda times x star. Then we multiply the first equation from the left with x star and the second equation from the right with x. Now, since H is Hermitian, H is equal to H star, and therefore the left-hand sides of these two equations are equal, and hence also the right-hand sides must be equal, and we have that x star times lambda times x is equal to lambda bar times x star times x. On the left-hand side, we can pull the scalar lambda into the front of this product, and then we can replace x star times x with the 2 norm of x squared in both expressions. Since the eigenvector x is guaranteed to be non-zero, it follows that also its 2 norm cannot be 0, and therefore we may divide both sides of this equation by the 2 norm of x squared, which yields that lambda is equal to lambda bar, so the complex number is equal to its complex conjugate, which means that its imaginary part has to be 0, or in other words, lambda has to be a real number. Moreover, we have the following spectral theorem for Hermitian matrices, stating that a Hermitian matrix has a full set of linearly independent, mutually orthogonal eigenvectors, and hence the Jordan form of a Hermitian matrix can be stated as H is equal to U times lambda times U star, where lambda is of this diagonal form and all of the diagonal entries are real numbers, and moreover U is a orthonormal, or in other words unitary matrix. For the proof of Theorem 10.7, we start with the result of Theorem 10.6 that H has n not necessarily distinct real eigenvalues lambda 1 through lambda n. The proof proceeds by going through this list of n eigenvalues and reiterating the same step for each eigenvalue, starting with lambda 1. First, for lambda 1, there must exist a non-zero eigenvector x1 such that h times x1 is equal to lambda 1 times x1. For any matrix, clearly the span of the eigenvector x1 is H invariant. For Hermitian matrices, however, also the orthogonal complement of the span of x1 is H invariant. This can be seen from the following little argument. We pick any vector y in the orthogonal complement of the span of x1, which means that the inner product of y with x1 is equal to 0. Therefore, also the inner product of y with h times x1, which is the same as the inner product of y with lambda 1 times x1, which by linearity of the inner product is the same as lambda 1 times the inner product of y with x1, is equal to 0. By the definition of the adjoint, the inner product of y with h times x1 can also be written as the inner product of h star y with x1, where now h star is equal to h because h is Hermitian, and hence the inner product of hy with x1 is also equal to 0. And this is exactly the definition of hy being in the orthogonal complement of the span of x1. Since the orthogonal complement of the span of x1 is invariant under the operation of h, we can restrict the operator h to the orthogonal complement of the span of x1 and define a restricted operator that we call h1, which maps between these two n-1 dimensional spaces. Thus, h1 has n-1 eigenvalues, which are exactly the other eigenvalues of the operator h, so lambda 2 through lambda n, and hence we may repeat the same steps as above for lambda 2, and then we define h2, and then for lambda 3 and so on, up to the last eigenvalue lambda n. So as a result, we get a full list of n mutually orthogonal eigenvectors, and hence the result stated in Theorem 10.7. As a corollary of Theorem 10.7, we have that the rank of a Hermitian matrix R is exactly equal to the number of its non-zero eigenvalues. For the proof of corollary 10.8, we first write H according to Theorem 10.7 as U times lambda times U star, where the rank of U is equal to n because U is a unitary matrix. By using Sylvester's inequality in Theorem 6.11f twice, we have that the rank of H is equal to the rank of U times lambda times U star, which by the first use of Sylvester's inequality is equal to the rank of U times lambda, and by the second use of Sylvester's inequality, this is equal to the rank of lambda. Remember that lambda is a diagonal matrix, and hence the rank of lambda is equal to the number of its non-zero diagonal elements, which proves the claim. Another important result about Hermitian matrices is stated in Theorem 10.9. A, the supremum taken over all n-dimensional vectors x of the ratio between x star hx and x star x is equal to the maximum eigenvalue lambda max of the matrix H, and B, the infimum over all n-dimensional vectors x of the ratio between x star hx and x star x is equal to the minimum eigenvalue lambda min of the matrix H. The proof of this result will be part of exercise sheet 11. An important subclass of Hermitian matrices are so-called positive semi-definite and positive definite matrices as defined in definition 10.1. In fact, a Hermitian matrix P is called positive semi-definite, denoted like this, if the following condition is satisfied, namely for any vector x in Cn, we must have that x star px is non-negative. And a Hermitian matrix P is called positive definite, denoted like this, if for any non-zero vector x, the expression x star px is positive. Note that analogously a Hermitian matrix N can be defined to be negative semi-definite, meaning that minus n is positive semi-definite, or to be negative definite, which means that minus n is positive definite. An important remark that often leads to errors is that only Hermitian matrices can be either positive or negative definite or semi-definite. In fact, if the black set represents the set of all n by n matrices, then the set of Hermitian matrices, shown in yellow, are a subset, and then the set of positive semi-definite matrices is again a subset of the set of Hermitian matrices, which contains the set of positive definite matrices. And in the same way, the set of negative semi-definite matrices is a subset of the set of Hermitian matrices, which is disjoint from the set of positive semi-definite matrices, and which contains entirely the set of negative definite matrices. Note that there also exist some Hermitian matrices in this subset here, which are neither positive semi-definite nor negative semi-definite, and these type of matrices are also called indefinite. Note that we can extend this notation of the calligraphic greater than or equal to 0, greater than 0, less than or equal to 0, and less than 0 in a way where we compare two Hermitian matrices, whether one is greater than the other or one is greater than or equal to the other. At this point, it's certainly recommended that you take a moment and think about why this notation is actually justified. Now, let's look at two examples of matrices A and B and ask ourselves whether or not they are positive or negative, semi-definite or definite. First, the matrix A is given by this 2 by 2 matrix, and in order to find out whether or not A is positive or negative, definite or semi-definite, the first thing we have to examine is whether A is Hermitian. And in this case, we see that A is a real matrix and it's symmetric, so therefore A is also Hermitian. Then we take any two-dimensional vector x with the elements x1 and x2, and we multiply A from the left with x star and from the right with x. When we perform these two multiplications, we obtain the scalar equation given by 2x1 squared plus 2x2 squared minus 2x1 x2, which can also be written as x1 squared plus x2 squared plus in brackets x1 minus x2 squared. Looking at this expression, we realize that x star ax is positive whenever x is not equal to the 0 vector, and therefore A is a positive definite matrix. In the second example, we consider the 2 by 2 matrix shown here, and again, to find out whether or not B is positive or negative, definite or semi-definite, the first question we have to ask is whether B is Hermitian, and here B is equal to B star, and therefore B is actually a Hermitian matrix. Second, in order to check the definiteness of the matrix B, we assume any vector x in R2 with the elements x1 and x2, and we form the expression x star times b times x given by this expression. Performing these two multiplications leads to the expression x1 squared plus 4x1 x2 plus x2 squared, which for instance is equal to 6 if we choose x1 equal to 1 and x2 equal to 1, and for instance it's equal to minus 2 if we choose x1 equal to 1 and x2 equal to minus 1. Since now we have obtained one positive result and one negative result, this means that B is neither positive semi-definite nor negative semi-definite, and hence B is indefinite. Hence, we can conclude from these examples that positive definiteness is not related to the entries of a matrix being positive, because in the first case of matrix A, we had some negative entries and still A was positive definite, and in the second case of the matrix B, we had that all entries are positive, but B was not even positive semi-definite. Now, this slide provides alternative characterizations of positive semi-definite and positive definite matrices. First, Theorem 10.11 provides an alternative characterization of positive semi-definite matrices, namely, let H be an Hermitian matrix, then the following statements are equivalent: A, H is positive semi-definite, and B, all eigenvalues of H are non-negative. And similarly, Theorem 10.12 provides alternative characterizations for positive definite matrices. In fact, let H be an Hermitian matrix, then the following statements are equivalent. A, H is positive definite. B, all eigenvalues of H are positive. And C, all principal minors of H are positive. Clearly, these theorems hold analogously for negative semi-definite and negative definite matrices. So in the case of theorem 10.11, if H is Hermitian, then H is negative semi-definite if and only if all of its eigenvalues are non-positive. And in the case of theorem 10.12, if H is Hermitian, then H is negative definite if and only if all of its eigenvalues are negative. The proofs of theorems 10.11 and 10.12 follow directly from theorem 10.7 and are therefore omitted. The only thing that's a little harder to prove is theorem 10.12c, but the statement is just included for the sake of completeness and we won't use it as part of this course. Nonetheless, it should be remarked that a principal minor of H is defined as the determinant of the k by k matrix that remains if n minus k rows and n minus k columns are removed from the matrix H. Recall that we have already discussed about minors in chapter 2. Further important properties of positive semi-definite and positive definite matrices are stated in lemma 10.13, where we suppose that P is a positive definite n by n matrix and Q is any n by m matrix. Then A, the square root of x star px, which is also denoted as the p norm of x, qualifies as a norm on the vector space Cn. B, q star pq is always positive semi-definite. And C, q star pq is positive definite if and only if the null space of Q is equal to the trivial null space containing only the origin. The proof of lemma 10.13 is again not very hard. For part A, all we need to do is check that the expression square root of x star px satisfies all properties of a norm as stated in definition 5.1. For part B, we need to verify two things. First, that q star pq is Hermitian, which easily follows by looking at q star pq in brackets star, which turns out to be equal to q star pq. And second, that for any vector y in Cm, we have that y star times q star pq times y is greater than or equal to 0. And this holds by defining the vector x as q times y. So here we obtain x star px, which is greater than or equal to 0 by the fact that p is positive semi-definite. And for part C, note that we have x star times p times x is equal to 0 if and only if the vector x is 0, and that's because p is also positive definite. Now, since by assumption the null space of Q is the trivial null space, this means that x, which was defined as q times y up here, is 0 if and only if y is equal to 0. And therefore, y star times q star pq times y is equal to 0 if and only if the vector y is equal to 0, which concludes our proof. Another nice thing about positive semi-definite matrices is that one can easily compute the square root of them. In fact, the square root of a matrix can be defined as shown in the equation at the bottom of the slide. In fact, for a matrix P, we are looking for another matrix denoted with P to the 1/2, such that if we multiply this matrix with itself, we get the matrix P. So if P is a positive definite or positive semi-definite matrix, by Theorem 10.7, we can write P as U times lambda times U star, where U is unitary and lambda is diagonal with only positive or non-negative real eigenvalues of P on its diagonal. Based on the spectral mapping theorem, we can hence define the square root of P as P to the 1/2, which is equal to U times lambda to the 1/2 times U star, where lambda to the 1/2 is a diagonal matrix that contains the square roots of the eigenvalues of P on its diagonal. Note that if P is positive definite, then also P to the 1/2 will be positive definite, and if P is positive semi-definite, then also P to the 1/2 will be positive semi-definite. The concept of the square root of a matrix will be revisited on exercise sheet number 11.